Okay. So this is where we were last time, I believe. Okay, just quick to pick up where we were in the class. We have these 5 other equations, which maybe we should just keep writing them and writing them. Maybe I will again in a second, but we have the 5 other equations, the 2 definitions, the definition of average velocity, definition of instantaneous velocity, definition of average acceleration, definition of instantaneous acceleration, and then the one other statement about average velocities, which I will write again in a second. We had those 5. They contained information, like new information, like 4 of them are definitions. So whenever you define something, that's new. And one of them was a consequence that is only true under certain conditions. And I'm going to write that again. Those conditions were constant acceleration. If we accept those conditions, if we accept that condition, constant acceleration, a change in a change, but not a change in a change in a change. And I'm serious, right? If we accept that we're looking at situations where there is acceleration, where there is a change in position per time, we call that displacement. So therefore there's velocity, and there's a change in that per time. There's a change in position with respect to time. Where we're looking at situations where there is that, but there's no deeper change than that, where the change of velocity remains a constant. That's the situation we're looking at here. Then we found last class or last videotape class or whatever, that there's 2 more equations, these 2, that pop out of the other 5. Like they're not new information, they're just taking the other 5 and smashing them together, really 3 of the other 5, and smashing them together algebraically to produce these. So technically we don't need these at all, but the reason we have them is because they're so incredibly useful as shortcuts for situations like, so let me, okay, so again, we don't want that. You can copy that down if you want. That's called the Dirac delta function. That is a very cool function, but not what we were doing here. This is supposed to be, I know I write this on, this is supposed to say if lowercase a equals lowercase a naught. So if acceleration is a constant, like that's the condition, then, okay, then we had equation number 5 is true. And these 2, the ones that I just wrote on the previous board, and notice again, and I'm being intentionally somewhat inconsistent or somewhat very, notice sometimes I have, well here, I'll write the equations again, and I just want to point out something. In these 2 last equations, you'll notice again, I wrote them slightly differently from the way I did last Wednesday. In both equations, I have this x naught term because technically it's there, because technically displacement is change in position from then to now, like displacement is x minus x naught. But I'm just cautioning you back on this page. I'm saying down here in blue that sometimes I won't write that x naught at all, because a lot of times, because x naught means wherever the thing that you're studying started. And that means relative to zero. Where is zero? Wherever you want, according to Galileo. So often, in fact, as often as we possibly can, wherever an object starts, we call zero so that we don't have to deal with that extra term, and we can do that. And Galileo allows us to do that. So frequently x naught equals zero. So frequently I don't even write it in the equations at all. Okay, I will be inconsistent about this because I want us to be fluid, dexterous. Often I won't even write that x naught term at all. And when I do, you can assume it's because I'm assuming it's equal to zero. That's what I'm saying here. But the reason sometimes I do write it, because it will become important, we do have to be clear in our mind, we're allowed to set zero wherever we want, wherever is convenient. And it is convenient to set it wherever an object starts. But if there's more than one object in the problem, which eventually there'll be, if we're ever analyzing more than one object at the same time, and if they don't start at the same place, then we need that term. So that's why sometimes I'll keep it and sometimes I won't. But that said, we now have these these equations are only true. Like notice, this is if and only if. These three equations are now only true if acceleration is a constant. But with those equations in mind, I'm going to give us all now one last exercise to do right here to see how we're doing. And it's based on the homework, and it's like the homework I'm going to do. Let's do one more here. But then I think if we're all good with it, we're actually going to move on to some other stuff. Well, that's what I want to say. Wait, so what I'm saying is we're about to do one more sort of the next step of exercise problem, whatever you want to say, in class, like we've been doing with the charts and stuff. We're going to do one more right now and see how we do, just based on all these equations. But that's assuming there's no questions before we do. Are there any questions at all about this? So not just about the material, not about, but you can hear me, right? Wait, can I just get some indication that you can hear me or that you're still there?
We can hear you.
Awesome. That was a very strong indication. Thank you. I appreciate both of you. Okay. Okay. So here's a problem. Actually, I'm lying. It's going to be two problems, not one. First. And again, these are taken straight from the homework. I'm just going about the homework problems sort of out of order so that people who did them will be rewarded, but people who didn't do them won't feel alienated. Okay, here's the given of this problem. And it is an exercise or whatever, something's going to fall from rest, like we've been talking about. It's going to free fall from rest. So it's going to accelerate at a constant rate, the rate due to gravity. And it's going to be from rest, which means V naught, no tricks, V naught equals 0 miles per hour, I'm saying. Now, I could say that this object free falls on the moon, and I could say it free falls on Earth and say, okay, as we're hopefully getting used to, therefore its acceleration rate in meters per second on the Earth is like approximately 10 meters per second squared. Like I could say that, right? Or if I want to be clever and cute or something, I could say, oh, but we're not on Earth, we're on the moon. where gravity is weaker, and that's true. And gravity doesn't pull you down with it cause an acceleration rate of like 9.8 or 10. It pulls down at more like 1.16, and that's true. And we could do a problem where we're on the moon and the acceleration rate is 1.6, and I could say that, and I could ask you to figure out things, and you could do it based on what we did last week. I want to do something a little bit in between. I'm going to say, no, we're on Earth, and we're being realistic. We're using the numbers and the metric system we use on Earth, but I really want to put this acceleration in perspective for all of you. So I'm saying that sure, we could talk about the acceleration due to gravity. We can say that it's approximately 9.81 meters per second squared, which we can round to approximately 10 meters per second squared. Or as many of you know, of course, there's something very convenient but not magical about meters. We could instead be like American about this and measure in feet per second squared. And if we did that, the number, of course, is different. There's a unit conversion, and we find that G is more like 32 feet per second. So people who can relate better to feet, you want to picture gravity as something when you drop something, it's at rest, and you let it fall. 1 second later, it'll be going 32 feet per second. A second after that, it'll be going 64 feet per second. And then a second later, like the third second, it'll be going like 96 feet per second. Okay, that's true too. That's just a unit conversion, right? That's just picturing it in feet rather than meters. But now I'm going to go a step further because we really do live in America, and people can relate sometimes to the way cars work in miles per hour and stuff like that better than they can relate to science class units. So I want to tell you what I'm saying right here. This is not arbitrary. If you do the unit conversion, first of all, I want everybody to understand, but second of all, I want you to solve a problem on this. If you do the unit conversion, another way to think about free fall is if you drop something from rest, let it go and like give it a long, long way to fall, like a long rabbit hole or something. If you drop something from rest, what gravity means is that 1 second later, it will be going 22 miles per hour. Again, that's just a unit conversion, like an annoying one perhaps, but you see it once you see it, it's indisputable. Something that falls, if it's falling 9.8 meters per second squared, that means by unit conversion, it's falling 22 miles per hour per second. Now, I'm not saying miles per second squared. I'm not saying miles per hour squared. I'm saying that if you want to put falling objects into like car terms, automobile terms, then when something falls, after 1 second, it's going 22 miles per hour. After 2 seconds, it's going 44 miles per hour. After 3 seconds, it's going like interstate highway speed, 66 miles per hour. I'm not saying that's like, whoa, but it kind of is to me. I mean, that puts it in perspective for me. Maybe that puts it more in perspective for you, maybe it doesn't, but it's a fact. So we're going to use that fact, and I'm going to say, okay, let's talk in those units just to see how dexterous we are. If we allow gravity now, and you can of course check the units on you. If I say this, then the question I want to ask all of you, and again, lowercase g, whenever I use lowercase g, it stands for the magnitude of that constant acceleration rate under free fall. Like g itself never has a negative sign. You put a negative sign depending on your coordinate system, but g is always, and g is this number. So I'm going to say, assuming this, question one that I want everybody to work on, like starting momentarily, whether I put you in rooms or not. Question one is, and this is a plug and chug in a way, like you definitely don't need anything but the equations. In another way, if you sort of think around and through the equations, think about what the equations mean, rather than just plugging in, you'll probably get the problem faster. But It definitely doesn't require anything but what we've been saying so far. So my first question is, if things fall at a rate of 22 miles per hour per second, then how far has something fallen in a minute? You also, by the way, you can get this by slogging very carefully through a bunch of unit conversions. And I shouldn't say slogging, but you definitely can just get it by being careful about unit conversions. But there is also maybe a faster way too. But so I want to know at the end of 1 minute, how far has something fallen in miles? Okay, and then the next question, I'll go back to that page in a second. But then the second question is, I want to know, um, um, okay, so it's two-part question. I think I want you to work on it. I think I may put you in rooms in a second, but I won't necessarily jump to that. Whatever it is, just to allow everybody to be quietly thinking on their own. I want these two questions answered. Again, you definitely don't need any equate. I'll write the other equations down in a minute too, if it helps. In fact, let's even say I'm not going to do breakout rooms because I want people to be able to see the board. We've got two questions here. I want everybody to please try right now, even on a blank piece of paper, whatever. The givens are v naught equals 0, lowercase g, which is to say a, right? I mean, I'm not trying to trick anybody. Like g is an acceleration, and it's the constant acceleration. And here we're expressing it in miles per hour per second. In a way, this whole problem is just one annoying unit conversion in a way, but there's ways to make it not annoying. So I want to know at the end of 1 minute, how far is this thing, well, yeah, so how far has something fallen given these facts above in miles within 1 minute? How far is it fallen? And then my second question B here is, how fast is the object going at the moment it has fallen 22 miles? Okay, I'll rewrite the whole problem again on the third page, but please start working on it now. I'm not going to put you in rooms. I just want to know. I want people to work on these. Could I get a show of hands that you understand what the question is? It's a two-part question. Could you just raise hands to show that you get the question? Or are people? Cool. Thank you, Justin. I totally appreciate it. Anybody else? Is he the only one? I'm dying out here. I'm dying too. Great. Thank you, Armand. I appreciate it. Okay, cool. So this is the question. I'm again on the next page. I'm just going to try to write the whole thing even more clearly, but it is just one question with two parts. Okay, so please start working on it. I'm just on the next page. I'm just going to start writing it again more clearly, but go for it. Oh, and let's say this, once you're done in any way, and I won't punish people for this. Once you either have two answers or know that you've hit a wall, like you've actually tried, you've got as far as you can, and you know why you can't go any farther, then either way, once you have an answer or you're just stuck and you now need discussion, but assuming you've at least thought about it, then please put up an electronic hand. Like once you're ready for discussion, and I won't call on anybody and challenge them, but I would like to know once people have actually given this enough thought that they want. So please put up your hand once you're either really stuck, like you've really tried things and you're stuck, and I won't call on you, or once you have an answer or two to share. But like everybody, right? Everybody with me? I'm going to write the problem again right now, but this is what we're going to work on to make sure we get this. And yes, watch the units, please. Okay, so this is the problem. So I'm walking away until. Can I ask everybody to look in the chat? Or I'm changing the rule now. Can you please raise your hand electronically if you would like more time? I just want to make sure that I haven't just lost everybody. So if you'd like more time, totally fine, but please raise your electronic hand. Raise your hand if you can hear me right now. Thank you, Sarah. I totally appreciate it. Thank you, Sarah. I totally appreciate it. Thank you, Alyssa. Thank you, Lydia. Okay, I know I sound like romper room, but okay. I just want to make sure, because this is a thank you, Justin. Okay, because this is always risky, right? I mean, I don't want to waste anybody's time, but I don't want to waste anybody's time. And I know I'm in everybody's living room, it's bedroom, it's crazy. But like, so I'm asking everybody to work on this thing, right? Not on this thing. What originally I was saying was keep working and take your time until you're stuck, and then raise your hand, right? But I'm also, but then I put in the chat, like, please raise your hand now if you want more time, just because I'm worried that everybody just walks away for an hour. So can I just get an honest, do we want more time or do you want me to talk about this? It's up to you guys, but like if you're actually thinking, then think as long as you want. Seriously, if you're doing anything, if you're looking on the web, do it, talk about it. Okay. All right, I'm going to go with Farina because she's the one person who said something. I'm going to talk about it. But I hope people really did, like we're all in this together. I hope you've legitimately thought about this problem before I talk about it. Otherwise, then if everybody's thinking about this and I'm talking about it, then we're going exactly at the right pace for the circumstances. But if I'm just talking and no one's thinking, then of course we're going too slow, and too fast at the same time. Anyway, all right, here's a situation. I'll tell you what the answer, I think the answers, well, here. These are all the equations we have so far, but the answers, I think the answer to the first one, I mean, does anybody want to volunteer anything? But the answers to the first one is 11 miles. I will do it out. Don't get me wrong. I'm not like trying to, but I just want you to know if anybody who did work on it, I want you to have the satisfaction or not. The answer to yes, awesome. And thank you for saying it. Oh, is that to everyone? Yes, that's awesome. And I believe it. In fact, so that's great. That means you really know something, Alyssa, and anybody else who got that. And thank you for actually, and I'm going to say the other answer, but just so we have it, but then I maybe want to hear either from Alyssa or from someone else or from myself about where the 11 came from. But the other answer, I believe, is approximately like, now in the other question, I believe, wait, was my second question, I think was, yeah, how fast is it going at the point where it's reached 22 miles? And I should have specified how I wanted speed to be expressed. I think it's most natural in this problem to express it as miles per hour. So I do think the answer to the second question is, you might express it this way. Sorry, you might express it something like this. You might even have expressed it in miles per second, in which case I think you get like 0.518. That probably wouldn't be as intuitive a way to express it, but it would be fair, very fair to express it this way. And of course, it's much smaller. So I think those are the two answers. But I want to hear if Alyssa or anybody else wants to talk us through how we got the 11 miles. Alyssa, do you feel like it or no?
Sure, I could explain it.
That'd be great. That would be great. Thank you.
So I use the equation x minus like initial x equals 1/2 a t squared plus initial velocity times t.
Awesome. Perfect. Great.
So for initial position, I put 0.
Awesome. Oh, I totally agree. Awesome.
So it'd be x minus 0.
Right. Okay. Right. Okay. Awesome. Keep going.
And then it's 1/2 22.
Right.
Times 1 squared.
Right. And I'm gonna put the units in just to put, yes, absolutely. Hold on one second. Yes.
And then it'd just be plus 0 times 1.
Absolutely. Yes. Plus 0. Absolutely. So, sorry. So just to everybody, but I'm going to interrupt for a second. Totally right. There's many ways to do this, but this is possibly the best way, certainly the most appropriate way to do this for where we are in the class right now, because this is the equation we just derived. last Wednesday. She's totally using it exactly for the right circumstance where we have the time and the acceleration and looking for the displacement. She's totally right to say, Alyssa's totally right to say that x naught could be set as 0. And she's totally right that we can multiply out the way we're about to. I mean, and she's totally right. Oh yeah, I said that. To set the V naught equal to 0, totally right. And by the way, I should say that to everybody. X naught, she is like setting to 0 correctly. She's saying we can call the very first place where the object started, we can call it 0 because there's no reason not to. And that's true. Then V naught, she's realizing is 0. Like, I just want everybody to see that there's 2 zeros that made this very convenient. But the one on the right-hand side, that's not even like a decision on Alyssa's part. That's a discovery or recognition. Like, that object started from rest, and we can't, in this frame of reference, change that as such. But all right, right. So then now she's going to plug in the numbers, which she can because she's doing it correctly because the units are actually correct. So, oh yeah, oh right. So I guess I'm well, so I think there's so keep going, Alyssa. I'm sorry if you.
After, because I put you would just get 22 times 1/2 or 22 divided by 2, which would give you the 11.
Right.
Because everything else basically cancels out.
Yes. Awesome. Awesome. Right. So she multiplies the half by 22 and gets 11. Totally correct. And then I want to do this a little bit carefully and the units do. Oh, wait. 1 second. Wait a minute. One thing. Well, I don't mean to correct Alyssa, but I do agree with all this, but let's remember one thing. The problem, one thing that either makes it easier or harder is the problem asked for how many miles will this thing have fallen within 1 minute. I just want to make sure to everybody. And this may be why, and she's still right. Everything Alyssa's saying is still right. And the answer is 11. But I'm just remembering now why some of you even might have tried to plug in or wanted to do it Alyssa's way, but then got stuck and don't quite see why it works out or didn't get 11. Because here at this moment, I want to be really careful. Like it's 1 minute of time that we're asking about, yet the acceleration is measured in miles per hour per second. So I'm going to just take over here. I'm still agreeing with everything. I just want to, but some coincidences work out nicely in a way that some people might have given up right here. It's basically what I'm saying to everybody. Like, what Alyssa is saying is totally correct and works. And also there are other ways, but this way does work and is right. But if we're really careful about it and we keep track of what's going on, it can look intimidating at this step. It can even look like one doesn't know how to go on, because I actually can't multiply that 1/2 by the 22 just right yet until I do something with all these crazy units that are flying around. Like, literally now I have miles and hours and seconds and minutes flying around. Well, the miles are okay, but I've got 3 different units of time flying around. So I've got to do something about that. One thing, and again, it's clearly this is okay and solid in Alyssa's mind, which is good. So I'm not trying to bore her or whatever, but some things that are not obvious, that you literally might not even know that you don't know, you might not know why you don't like the look of something when you look at it. I would look at this second line and I would be intimidated. I wouldn't even know what to do next in a certain frame of mind. Because one thing might not occur to me, that miles per hour over seconds is one way of writing what I've written down here. Like, the hours and the seconds are both in denominators, in the denominator. And it does make it a little bit easier to see things if you're aware of that explicitly. So now I have this, because now I can say, okay, wait a second, I've got all these time units and I've got to do something with them. It really isn't fair just to ignore them. Like, something is mixed up about all these units. But if I go slow, like, okay, the problem wanted me to know how far something would fall in a minute. So I'm focusing on those minutes there that are getting squared, right? They're even getting squared. So let me try to convert everything into minutes so I can be okay. Like, in other words, I'm going to say, all right, I've got 22 miles per hour per second. But if I multiply that by 1 hour over 60 minutes, right? If I do that, which I should do and I can do, I will get rid of these hours and I'll have minutes in the denominator, right? Which takes care of converted. That's how I can convert that hour unit into a minute unit. And now at least instead of having hours, seconds, and minutes squared, I have minutes, seconds, and minutes squared. So that sounded a little bit better. And let me do it one more time to get rid of the seconds and watch what's going to happen. Like I should now, according to this unit conversion right here, before I go any further, I should, there's a 60 down there in the denominator. I should like literally divide 22 by 60 to get the number. And maybe I can't do that on my head. But notice that now if I do this one more time, if I do times 60 seconds per minute, right, in order to cancel out those seconds and be left with all minutes in the denominator. Now, this is why what Alyssa did worked, but I want to make this clear to everybody. Look, the question, this thing speeds up at a rate of 22 miles per hour every second. 60 seconds later, like a full minute later, I want to know how far it's gone. So what I've done is I've converted the hours to minutes by divided by 60, and I've converted the seconds to minutes by multiplying by 60. So of course, I don't even have to bother. I notice, oh yeah, I've got a 60 in the denominator now and a 60 in the numerator now. So now I literally have now I literally have something that, first of all, makes sense. I have a 1/2 AT squared where the units are all consistent. The A is 22 miles per minute squared, and the T is in minutes. Like this is looking more, now the units are not all mixy like they were before. This looks like, for example, 9.8 meters per second squared. So now I got something nice and solid. And now if I just, and the minutes squared will cancel with the minutes squared. So I'll get, just like Alyssa said, 11 miles. But now I want to back up and point this out to everybody. Like, look, if I am saying the acceleration due to gravity, so I'm saying you can think of the acceleration due to gravity as or this, or this, or this. Accelerations don't have to be with square time units, but when they are, they're very handy. Like if you, in the same, whatever you are starting to believe about the number G, 10 meters per second squared, you can believe also about the number 22 miles per minute squared. As long as you totally understand them, then that means, and this is the ultimate takeaway. So if I just want to say for like the 90 million bajillionth time or the 90 million bajillionth way, and again, because this is so important and so elusive, so easy to miss, not because anybody's not paying attention or blah, 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 but like what Alyssa is really saying here in the end, and it is true, she is right. She's saying if something accelerates from rest at a constant, sorry, can you even see, wait, sorry. Yeah, if something accelerates from rest at a constant rate of 22 miles per minute squared, if you actually get what that number means, you will immediately see that in the first minute of its motion, it will not travel 22 miles. Like that is that is really what Alyssa is saying. And it is correct. But I want to say it again, something that accelerates from rest at a constant acceleration rate of 22 miles per minute squared will not in the first minute travel 22 miles. It will travel 11 miles, half of 22. Just like something falling, if you measure in the traditional meters, if something's falling at a rate of 9.8 meters per second squared, in the first second, it will not fall 9.8 meters. It will fall 4.9. That's like really what I'm trying to say to everybody. That's like the kind of surprise, like you really, if you just think distance equals rate times time, you would never think that. But once you, maybe not never, but people tend not to. But if you really think this through, you will see that this is the difference between acceleration and velocity, that when something if something velocitizes, moves at a rate of 9.8 meters per second forever, then yeah, every second it travels 9.8 meters. But if something accelerates at a rate of 9.8 meters per second squared, forever, then at the end of from rest, then at the end of the first second, it will not travel 9.8, it will travel 4.9. That's the kind of thing where you either want to make sure you get, or if you don't get it, admit to yourself you don't get what I'm saying. And every time I say it, if you admit to yourself you don't get it, at least privately tell me that or do something about it, because you need to get it. So the answer to question one, and I know we run out in 4 minutes, so I'm just going to do the second one real fast, and then we're going to go, and we're just going to keep going like this, like we're just like, let's just get this physics. And I will post everything and blah, blah, blah. But the answer to the first question is, and again, thank you, Alyssa. And I'm not trying to make a big deal about any one person, not Alyssa or anybody else, but anybody that can contribute in any way to the discussion is a big deal in this class and in my life, because it helps. Because I don't want to be such a big deal in anybody else's life, and certainly not in their bedrooms. And thank you all for staying on the periphery of mine. So the answer to the first one is 11. And the answer to the question, what the heck have we done in physics so far, is these 7 equations. 7? Yeah, 7. And the answer to the second question, to 2, I mean, the answer I've already said. I think it's about 1,800 and change miles per hour, which is very, very fast. We're asking how fast is this thing going by the time it's hit 22 miles, right? That's the second question. Well, I'll write it again, like at X, and I keep putting in parentheses or Y, because some of us, it makes, if you're thinking of an up-down thing, to some people it might make more sense to use Y, and that's totally, totally fine, whatever. But at X equals 22 miles, I wanted to know what's the speed. Now it's very easy to think. Now remember, I'm trying to keep this problem simple, not easy, but simple. The simple fact is we've got something accelerate, and I'm looking at the time, but the simple fact is we're looking at something accelerating at 22 miles per hour per second. And I'm asking about like something about it when it's achieved 22 miles of distance. Well, it's very easy to think, oh, well, that'll be in the first second. Let's just find out how fast it's going at the end of 1 second. But no, it has not traveled 22 miles in the first second. First of all, it hasn't even traveled 22 miles in the first minute, we just proved, Alyssa just proved. But it hasn't even done that in the first minute. So it certainly hasn't done in the first second. So you might wonder, well, what time is it by the time it's reached 22 miles? Like if I could get that time, then I could get the velocity. And yes, you could do that. You could use any of the equations we have so far and use them one at a time to first get the time. We could first solve for time. And then from that for V. But just like Alyssa did, I'll say her name no more times. We could instead use one of these new shortcut equations, one of the equations that does that work for us. Like we could solve for time first and then plug time in for V, or we could have already done it in the algebra before we ever knew these numbers, which we did, and come up with this equation. Sorry, and come up with this, and this is what we're going to do. We came up with this equation last week, and this is just a little quick practice in using it. We came up with this equation right now, and we're assuming in this problem that the object starts from rest, right? So in this problem, and starts at position 0. So here is a perfect situation where we're not being asked the time and we don't know the time. So we solve, so we're solving for V based on what we know. So I'm just going to rearrange. In other words, we have this, right? Because I took out the 0 terms. So now some people might plug in numbers now and then rearrange. I advise, part of the lesson of physics is no, it's actually in the long term better to rearrange algebraically and then plug in the numbers. So what I mean is I'm looking for V, right? So V squared equals 2ax. Like I multiply both sides by 2ax, square root both sides. So I say find V equals the square root of 2ax or 2ay, whatever you like. 2 is the number 2. A is 22 miles per hour per second, and X is 22 miles. Yes. So right there, you see, we're just about to end. We're just about to end. Right here, this is like, so like what Alyssa did before. She picked the right equation. She arranged it correctly. She put in the right numbers. Now, I guess what I'm advising is it's really good to put in the units too, because sometimes you can get lucky and get away with the numbers working, even ignoring the units, which is kind of what happened last time because we had to multiply by 60 and divide by 60. So the units turned out to correct themselves. But here, it's not quite that way. Here, I see miles and miles, but I see miles per hour over second. Yeah, and I don't want that. We'll put it another way. What I have, and I know we're just, we have miles per hour per second. And then we have the 22 miles. So what we need is to change either those hours into seconds or those seconds into hours so that we end up having miles squared over seconds squared, and then square root the whole thing and you have a speed, or miles squared over hours squared and square root the whole. We have to do one or the other. So what I choose to do is multiply everything by 60 by 60. I'm saying this fast because we have to run out of because class is over. I multiplied by 60 and by 60 again. I'm just saying that I multiplied that 22 so that I had miles per hour squared there multiplied by miles. And so that's why I'm skipping the calculator step here because we have to go, but I got this. Which is very fast. But okay, class is over. Thank you guys. I hope you got something out of that. I hope if you did follow, I think that was something. We'll continue in 2 days. Yeah, I'm going to go because the next class is about to come in. Thank you guys very much. So, I mean, is that clear at all? I shouldn't even ask. Okay, bye, folks.